A probability distribution for a particular random variable maps the sample space to the probabilities of the outcomes in the sample space. So basically that's your input and the output. The input is the uh, the samples. The output is the probability of that event. And we kind of think of it like this: x is the event, p of x is the probability of that event happening, right? The easy one to think about here is the probability of flipping heads on a fair coin is 0.5. Notice when they're talking about this, they say fair coin a lot. Uh, People have actually done research. One, I can't remember which side it is. I think it's tails is slightly heavier on a quarter, so it's actually not a fair coin. But it's one of those things. It's close enough. It doesn't really matter. All right. A couple of things about a probability distribution. You can figure it out theoretically or experimentally. It can be discrete or continuous for both of those situations. Uh, the probability, and this one is pretty important, has to of any like event, it has to either never happen, always happen, or somewhere in between. A probability of 0 means it cannot happen. The probability of 1 means it always happens. I'm on Earth. The probability of me dropping an object and it falling to the ground is, or falling down towards the center of the Earth is 1. I can't drop things and have it go up in the air without some other force acting on it. And even then, it's eventually going to fall down anyways. So, um, the probability of uh, me opening up a can of soda and having the soda turn into gold as I drink it, that's a 0. That ain't gonna happen, right? So that's the idea there. But opening up a can of soda and finding pieces of metal inside of it, yeah, that could happen. They could have a manufacturer error. I'm sure it's happened to some poor soul out there. Um, and here's the other thing: the sum of all the probabilities have to add up to be 1. Take, for example, the probability of heads and the probability of tails on that nice fair coin. You add up those two probabilities, 0.5 plus 0.5, what do you get? 1. It's basically saying if you flip a coin, one of those two things is going to happen. And that makes sense. But all the probabilities should add up to 1. All right. Example 2. We're going to construct a theoretical probability distribution. X represents the sum of values on 2 dice. So you have 2 dice, 6 sides. Uh, and, well, let's make that 4 there. Now, when you roll these 2 dice, what can happen? Well, you can get really lucky, or really unlucky, I guess, and roll snake eyes. What is 1 plus 1? Well, that would be 2. Uh, how many ways can that happen? Well, that can just happen with 1 plus 1, right? So I'm going to actually make a quick little table here, and we're going to count all the different things that can happen. 1, 2, 3, 4, 5, and 6. This is going to be tight in here, but I think you'll get the idea. 1, 2, 3, 4, 5, 6. I gave it a little bit more space left and right. So here's the idea. In each of these boxes, we are going to add these two numbers together. 1 plus 1 is 2. 1 plus 2 is 3, 4, 5, 6, and 7. Okay, that makes sense. Now let's do the 2's. 2 plus 1 is 3. 2 plus 2 is 4. 2 plus 3 is 5, 6, 7, 8. you kind of see the pattern happening here? 3 plus 1 is 4. 3 plus 2 is 5. 6, 7, 8, 9. 4 times 1 is 5. 4 plus 1 is 5. 4 plus 2 is 6, 7, 8, 9, 10. And I'm just going to fill it out here real quick. I'm basically writing out every different possible combination of all of these events happening. 7, 8, 9, 10, 11, and 12. Now, how many are there? Well, there's 6 possibilities on the first dice, and there's 6 possibilities on the second, so a total of 36 possible outcomes. Okay, so we're going to come up with a relative frequency table here. So what are the outcomes? It looks like the lowest outcome is 2 and the highest outcome is 12, and we get everything in between. So 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I'll slide that over a little bit so it's not too close to the table. Now, how many times does a 2 appear in this table? Well, that'd be once. That would be one of the 36 outcomes. How about for the 3? Well, that looks like 2 of the 36 possible outcomes. For the 4, that would be 3 of the 36 possible outcomes. 5, that would be 4 of the 36. 6, 5 of the 36. 7, 6 of the 36. Well, I'm going to actually highlight that one because that one's kind of important. 7 is the most likely number to roll because that's the most out of all of them on the list. If you notice that the next number up is an 8, there's 5 of them. So I go back down to 5 out of the 36, 4 out of the 36, 3 out of the 36, 2, and 1. So that's the probabilities of each one of those things happening. And do a quick little check here. Add up all those numerators. 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 5 plus 4 plus 3 plus 2 plus 1. Guess what you get? 36, which would get you a total of 36 over 36, or a probability of 1. All right, awesome. Now, let's graph the theoretical probability distribution. For that, I need myself some axes. And you know what? I actually think I need myself a little bit more space here as well. So let's see. I think I see the highest number on here is the 6 out of 36. So you know what I'm going to do here? 1, 2, 3, 4, 5, 6. All right. Well, there's 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. One, two, threes, fours, fives, sixes, sevens all the way up at the 6, 8s, 9s, 10s, 11s, and 12s. There is my probability distribution, made in a nice little histogram shape. All right. Hey, wait a second. Let's scroll back up real quick. Oh, dang, look at that. That's the same exact shape that we had up here in the beginning. Who would have thought that they would have already have given us the answer to that? This is a pretty common one. You should probably basically know this one if you want to be taking a statistics class, or for the SAT, you'll probably get asked this kind of question.